Welcome to lecture 16 now. We looked at the flow nets, how to draw them, and using flow nets we can calculate the amount of discharge through the medium very easily. You can also find out the potential or the head at any point. Let's look at our simple problem again. We have a pervious stratum with a reservoir sheet pile as a cutoff, and we have the head loss is H0. Let us try to draw a descent flow net. Please remember the flow lines have to be orthogonal to the equipotential lines, and then we'll try to draw the equipotential lines. It's not a perfect one, but you can see it's a reasonably good one. Each of these elements are approximately good squares, as you can see here. Maybe I should move it a little higher, and you get it. I would like you to now visualize the region between two flow lines. Suppose if I do that, let's say this is one flow line and this is another flow line. So obviously this is flow line 1 and this is flow line 2. So you can say the flow is taking place through all these elements. Let me call this element 1, 2, 3, 4. Now let's say this head here, H1, H2, H3, H4, H5, etc. I would like to calculate flow through element 1, flow through element 2, flow through element 3 and 4. And from continuity condition, you will agree that whatever is flowing here will have to flow through element 2, 3, 4, etc. because they are bounded by two flow lines. The flow is contained by the two flow lines. So there is a continuity of flow along all these flow lines. And let's look at the distance between the two equipotential lines and the distance between the two flow lines. Suppose I say this is L1. You will have to agree if the distance between two equipotential lines is L1, within each element, the distance between the two flow lines also will be equal to L1, because we are saying each of the elements is a square. If I take element 2, this is L2 and this is L2. L3, L4, etc. The distance between the flow lines is equal to the distance between the equipotential lines. You agree also that as the flow takes place, the head keeps dropping. So if the equipotential line bounding the left of element 1 is H1, the equipotential line to the right of element 1 is H1, but to the left of element 2 is H1, to the right of it is H2. So it keeps changing. I'm sorry, here H2, H3, H4. This is, to the left of it is H1, to the right of first element is H2, to the left of element 2 is H2, again right of it is H3. So the head drop is the same because they are all equipotential lines. So let us look at this particular flow. Can I say the flow delta Q between two flow lines is equal to permeability Ki into A. This is the standard Darcy equation. K into I gives me the velocity, into area gives me the area, so that I get quantity of flow, the rate of flow. Can I say this is equal to K? What will be the gradient in element 1? The head on the upstream side is H1, the head on the downstream side is H2. So the head loss is H1 minus H2 divided by what is the distance traveled is L1. And can you tell me what will be the area of flow? And you can see here this distance is L1, and imagine a unit distance perpendicular to the board. So if I look at it, can I say it is L1 into 1? Please remember, you are looking at a two-dimensional problem. You have a sheet pile going long perpendicular to the board. So you have a river, let's say 1 kilometer wide, and you have put in a barrier right across that. So I'm now looking at 1 meter width or a unit width perpendicular to the board. So what will be the area of cross section? The distance between the flow lines is L1 into 1. Can I say this is equal to Q1? It's also equal to Q2, which is H2 minus H3 by L2 into L2 into 1. When you are calculating the flow through the second element, what is the head loss from the upstream to the downstream side? From H2 to H3. So that is H2 minus H3. And what is the distance of travel? Is L2. What is the area of flow? This distance is L2 times 1 gives me L2 into 1. That is the area. Similarly, third element, fourth element, etc. K into H3 minus H4 by L3 into 1 is K into H4 minus H5 by L4. Like that, you can keep on writing for any number of elements within the two flow lines. Agreed? So you can see that because the continuity of flow, whatever is the flow, delta Q is equal to delta Q1, delta Q2, Q3, Q4, Q5, etc. They are exactly the same. So in that case, can I now simplify and say that K, L1 cancels, we'll simply get etc. So you can see that the continuity of flow is satisfied, and what you will find is that permeability times the head drop between any two equipotential lines gives us the discharge. Suppose we now define that each drop is equal to total head by number of drops. So here you have, let's say the total head is H. We have one drop here, 2, 3, 4, 5, 6, 7, 8. So when I say ND is equal to 8, can we say that the head has dropped from H0, I call it, let's say 100%, by 1/8 here, 2/8, 3/8 by 50%, 5/8, 6/8, 7/8, and 100% drop. So can I say that H1 minus H2 is equal to H2 minus H3 is equal to H3 minus H4, etc. is equal to H by number of drops. The head drops in this case is 8. So we can see that between two equipotential lines, the drop is equal to 1/8 of the total. So now you know this is equal to delta Q is K times H0 by the number of drops. Is it clear? What we said was the continuity of flow is satisfied by the simple Darcy's law, K into I into A. K is the coefficient of permeability. The gradient is the drop between two equipotential lines divided by the distance between the two lines. And the area of cross section is the distance between the two flow lines times 1, which is the length or the distance perpendicular to the board. But since we have a flow net which has a square pattern, you can say that the distance between the two equipotential lines and the flow lines, these are the two equipotential lines and the flow lines are the same, and you cancel L, and you will find that the flow is controlled by K times the net difference, potential difference. And this drop, again, because we are dividing into a finite number of equipotential lines or nets or areas, I can say that depending on the drops, head drops from 100% to say let's say 87.5, 75%, 62.5, 50%, 37.5, 25, 12.5 and 0. So head drop across any two consecutive sets of equipotential lines is equal to the total head loss divided by ND, where ND is the number of drops. Please note that. Now this is the flow through one flow channel that is between two flow lines. Now how many such flow channels are here? I can see that 1, 2, 3, 4. You can see the flow is taking place here, 3 and 4. So the number of flow paths is 4, and so the total discharge is equal to delta Q into number of flow paths. So finally you will get, it's very easily Q is equal to K into H naught, number of flow paths by number of drops. A very simple expression, as long as we are able to draw a good flow net. The characteristics of flow nets are they should consist of flow lines and equipotential lines, and all of them should intersect orthogonally. Even here, please remember the downstream face or downstream surface is an equipotential line. So all the flow lines will have to come perpendicular to that. Similarly, they take off perpendicular, and the shape of each element is approximately a square, which means you are saying the distance between the two sides or midpoints or the diagonals are approximately same. Or another way would be, I try to fit in a circle which will touch all the four sides. If you can satisfy that, you get a perfect flow net. And if you have a perfect flow net, the flow through the flow net or the discharge through the medium is very easily calculated as coefficient of permeability times per unit area, of course. This is per unit area per unit time. The coefficient of permeability times the head drop, the net head drop. This is the upstream water level and this is the downstream water level. And the difference between those two is called H naught, or you have termed it as H naught, times number of flow paths. So here NF is the number of. So this is how we easily calculate the flow. Similarly, let's say I want to find out what is the head drop or the head loss at any point. Let's say this is O. What will be the potential or head? I can easily interpolate between any two equipotential lines. As you can see here, this is the 87.5%, this is 75%, this is 62.5%, this is 50%, and this is 37.5%, and this is 25%. Now you can immediately judge that the potential here will be between 37.5 and 25, maybe making an adjustment, maybe somewhere around 31%. So I can immediately say that at this point, H, if I call that the head, this is between 37.5 to 25% of H, and using your eye judgment, you know that it is somewhere close to half. You can estimate either way and say it's approximately equal to say 31% of H naught, or I can say is 0.31 H naught. Suppose I want the potential at some point here. Let's say I call that point as some M. Can you tell me what it's likely to be? The head here is 100%. The next equipotential line, because there are how many drops? 1, 2, 3, 4, 8 drops. So this will be 87.5. This is 75. And so it will be somewhere between the two. So it's between potential H at point M is between So using your judgment again, you can say here it's approximately equal to maybe 79% or 70. So you are now able to find out the flow through the medium and the potential or head, or if you want to call it head loss. The head here is 100% and it has lost by about 21% here, 50% here, by about 69%, 100%. As you go along the flow line, you can easily estimate the head loss with this flow net. Let's see another flow net for the weir or the barrage with a cutoff. I have the top boundary here, the bottom boundary. We have the weir here, and let us say you put in the cutoff somewhere here, and the upstream water level and the downstream water level are defined, and the head loss between the upstream and downstream, the width of the weir is V and the depth of the cutoff is S and the thickness of the stratum is T. Let's draw the shortest flow line. It starts from here, goes along the sheet pile, comes down, goes along the bottom of the weir. Then let's look at, just as an approximation, we have drawn flow paths. How many? 1, 2, 3, and 4. So you have flow paths defined. Now try to draw the equipotential lines. Now you can see the flow net is not symmetric. The cutoff is put in somewhere between the center of the weir and the edge of the weir, and you will now find that how many equipotential flow elements are there, or head drops. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So can I say the net head drops are 9? How many flow channels are there? 1, 2, 3, 4. So number of flow paths is 4. As long as you are able to maintain a rough square shape, this is a very good one. Maybe I should have changed it slightly here. In the presentation, I'll show you more accurate ones. We cannot draw it within 5 minutes. A good one, you have to keep practicing any number of times to get this flow net correctly. All that we do here is that make sure we satisfy all the boundary conditions and the main characteristics of the flow nets, which means the flow line will start from the upstream boundary orthogonally, will go along the sheet pile for the shortest one, and then go along the bottom of the weir, and the longest path will be along the bottom of the pervious stratum, and all others will be intermediate. Maybe something like here I can do that. And the equipotential lines are then drawn to make sure each element is approximately a square. So in this case, what you have seen here is very easily, within about half an hour, you can make a good flow net. I suggest that you practice as many as you can to pick up on the paper and derive the solution. And now I can say the discharge or flow through this medium is equal to K into H naught 4 by 9. The number of drops is 9 and the number of flow paths are 4. So straight away you are able to calculate the amount of discharge through this medium. And if you find that this discharge is too high, you can immediately take it down and then draw the flow nets, and then you will suddenly see that you may have to increase the number of drops, which means the discharge will decrease. So that is how you can design an engineering structure, saying that by increasing the distance S with respect to T, S by T ratio tends to 1, I can reduce this completely, the loss through the foundation. So this is the principle of flow nets, and by hand you can easily do the whole exercise. Now we have another set of problems wherein we would like to know a flow net through a dam. Here the weir or the sheet pile is impervious. But suppose I have a dam and assume for the time being it's on a impervious layer. So we'll call them as earth dams. These are one of the oldest structures we have been using in India. Practically every village used to have a storage reservoir in the village, to have pond we used to call them, and then we store water for the lean season. We don't get water all through the year. We only get in the monsoon period, maybe starting from mid-June to end of September or mid-October. If you build a earthen embankment, usually we do with a fine-grained soil, which means it should be silty clay, maybe with some sand, sandy, silty clay, sandy, clayey, silt, etc. The whole idea is this has to have low permeability. K of this generally is less than 10 to the power of minus 6 centimeters per second, because you don't want to lose the water. If the permeability is high, there is no point, because all the water will escape. So what you need to do is find out the right type of soil. When you compact it to maximum dry density, that's why we studied at optimum moisture content, I'll get the lowest permeability and I compact it in layers. So let us say this permeability is K, and the storage here is the upstream water level and this is the downstream. Now you can see that as far as the flow line is concerned at the bottom, I can easily define. But what about the uppermost one? Do I know anything about the flow line? And you can see that possibly this could be the upper flow line. Do I know it in the beginning? We don't. And this is called the phreatic surface. And this being the topmost flow line, that means the water will flow from C to D and from D to B along the slope surface. Can you tell me what is the pressure in the water at point C? It is exposed to the atmosphere. So can I say the pore pressure is 0, and at point D again it's exposed to the surface. So phreatic surface is the surface along which pressure head is 0. Basically it's atmospheric, which is what we take as datum. The pressure head is 0, which means if I am now taking this ground as a datum, can I say the potential at any point is simply equal to the elevation head? Please remember, a phreatic surface is the topmost flow line in a medium in which flow is taking place. The characteristic is that the potential or the pressure head, is 0 at any point, which means the total head is equal to the elevation head. This is 0, so you have the head keeps dropping as we move from C to D. The potential keeps dropping, and we need to find this surface. We make one simple assumption, which is given by a Frenchman called Dupuy. The last T is silent, and he somewhere around 1885, he said approximately the gradient is equal to the gradient of the phreatic surface for flows along relatively horizontal or not too steep lines. It's called Dupuy's assumption, which says I is equal to, so let me draw this in a slightly enlarged fashion. that is due to its approximate assumption. If you can determine this phreatic surface with this characteristic, it becomes very easy for us to draw the flow net, because you have both the flow lines bonded and I have an equipotential line, and I can simply draw these equipotential lines. I draw the flow lines and the equipotential lines, I get the flow net. So the most important part for flow through a dam is to find out the top flow line. Another way we define these problems is, it is called unconfined flow, whereas earlier we were looking at confined flow. When we are looking at flow through a pervious medium with a cutoff, we know that the flow is all bounded by these two planes, so it's called confined flow. When you have a dam, the top surface is not known beforehand, and we have to define using some characteristic. So based on that, we define the problem as an unconfined flow, and in the case of unconfined flow, this phreatic surface has to be found out, has to be determined. How do we do that? There are some approximate methods which are given. Let's take them. Flow through. First, let's look at homogeneous dam, which will be an unconfined flow. We have an impervious foundation layer, so we are assuming no flow through the or below the earth dam. So the upstream water level is here and the downstream water level here. So the net head loss, let's say, is H. The height of the embankment is HE. Always we design HE is greater than H, and this difference is called the freeboard. We never want the water level go to the top of the dam, then there is a possibility of breach and failure, so we do not want that to happen. If that is so, HE should always be higher. Now what is being suggested is that in order to determine the top flow line, let's say the distance, horizontal distance from the A to, let's say, B, AC is equal to delta. That will be equal to, basically, can I say, if the height is H, BC, H by BC is tan beta, so can I say BC, which is equal to, sorry, AB, AC is BC by AC, BC by AC is equal to tan beta. So delta AC is equal to H cot beta. This is the height H. I want to know this. Take a point here which is 1/3 of delta. Shall we call that point D? And let us say the phreatic surface is meeting at a distance L from the toe. This point let's call as E, and this is F. Then we'll have to draw the top flow line. I do not know L to start with. We had to find out the point at which the top flow line will meet the downstream face. Now can you see here? Again, I have a triangle EF, and shall I call this a G? And then you can see here the slope of this line, which is tan alpha is equal to FG by EG is equal to tan alpha, which is the, and can I say the flow is taking place here along the slope, so that will be the gradient I. the flow is taking place at that point along I. So can I say that from Dupuy's assumption, Q is equal to KIA. So K, I is nothing but dz by dx, and any point here the height is z, and in this case this is L, so this will be L sin alpha. Fg into 1, so this is K dz by dx into L sin alpha, and Fg by Ge is nothing but tan alpha. So this is equal to tan alpha into L sin alpha. So flow is equal to K into L sin alpha tan alpha. The flow into this small triangle, that is what it is going. Let us try to find out the flow at any other point. The height here is h, so the flow path is c into 1 and the gradient is dz by dx, which is what Dupuy's assumption is. So Q is also equal to KIA, which is K dz by dx into z into 1. Can you follow? Whatever flow is taking place through the embankment, the continuity has to be maintained. So the amount of water that is entering is going out through this face FG. It's entering through AB and it's exiting through FG, and then it will flow along the slope and go down. So we have continuity of flow. The flow here is given by the height is Fg, which is L times tan alpha. The gradient is tan alpha. I'm sorry, this is sin alpha. Fg is L times sin alpha, and the gradient is L dz by dx, which is tan alpha. So we equate these two and then integrate from left to right so that we can solve for L. So what we say is that Q is equal to K dz by dx into Z is equal to KL sin alpha tan alpha. And can I write it as, of course we can cancel K, you get dz, Z dz is equal to L sin alpha tan alpha into dx. And let's integrate from, the limits are, as far as Z is concerned, L sin alpha here to H, and on the right side it is from L cos alpha, this is L cos alpha, times this distance d. How do we define distance d? That is from the bottom up to this point. The distance from here to here, or I'm sorry, here, the toe of the dam. And if you solve for that, we get L is equal to, very simply, d by cos alpha minus square root of d square by cos square alpha minus h square by sin square alpha. Now this distance from D to B is delta by 3. From here to here is the embankment height, and then we can draw the figure and calculate. You can very easily calculate this distance d. We know the head loss h, and the downstream slope is inclined at an angle alpha. So if you do this, you can calculate the point at which the phreatic line hits the downstream slope, and then it's supposed to be a parabola here. What we do is that we make a slight transition and do this. After that, we simply draw the equipotential lines and the flow lines. You can see here now you got a very simple flow net once you determine the phreatic surface. And in order to do that, you have to calculate this length L, the height or distance from the toe where the top flow line comes and meets the downstream face. And even here, once you get the flow net, Q is equal to K into head loss, number of flow paths by number of drops. In this case, how many? 1, 2 flow paths are there. How many head drops? Please remember, this is an equipotential line. 1, 2, 3, 4, 5, 6, 7. 7 head drops are there. By the time it comes, it's flowing down. So we say number of drops is 7. And once you have that, you can calculate the flow. Similarly, you can calculate the head drop, because basically this equipotential line is hitting the downstream with the phreatic surface here. So the potential is equal to simply the elevation at that point. Shall I say Z? So if you know the height of the phreatic surface, the potential is corresponding to the top of it. The only point I'd like to mention is we never design an embankment with phreatic surface touching the downstream face, because once the water comes, this part of the soil becomes very soft and it will start collapsing. So what we try to do is introduce a drain. So here is the dam. Suppose I provide a drain. What you find is that the phreatic surface will not go. This is what you call a gravel drain. This is impervious. You do not want the flow line to go to the downstream face, and it will not go downstream because you have a highly pervious material. K here is around 10 to the power of minus 3 centimeters per second, or even 10 to the power of minus 2. Whereas the embankment is 10 to the power of minus 6 centimeters per second. This is called a blanket drain, or you can have a toe drain. You provide a triangular one so that the flow line will come and meet not on the downstream face but inside. This is called a toe drain. And we use very similar construction in order to find out the top phreatic surface, starting with this value here, and I can find out the top phreatic line. Then I get the flow net, and then rest of it is exactly same as for confined flow. Even here, you can see here, and we draw the flow net, and you can easily solve any problem. And we'll see also in the next class how to do if the foundation is also pervious, and how to calculate upgrade pressures, etc.